Start off today with a little bit of review and maybe applying some of the concepts we've learned in the last week into some larger, more complex problems. One of those applications looks something like this. So let's take a four-sided figure here, and I'm going to tell you that this angle is 58 degrees. And I'll tell you this side over here, call this 35 feet, and down here we'll call this 40 feet. And let's see, up here we'll call this one 31 feet and 32 feet. And I want you to find the area. Well, to find the area of this figure, we need to get it cut in such a way that we have shapes that we can find enough pieces to do the area. The logical shapes that we usually cut things in are, first of all, rectangles, but there's really nothing on here. We don't have any marked right angles here. There's nothing on here that would indicate a rectangle. The second option is usually a triangle, and we can do triangles here. In fact, in this case, if I cut it across here, I already have one triangle that I can find the area of. This triangle right here, I can find the area of. That's going to be 35 feet times 40 feet times the sine of that 58 degrees, all divided by 2. Because that is two sides in the included angle, we can use that to find the area of that triangle. So I'm going to do that. Make sure my modes are correct here. They are. So 35 times 40 times the sine of 58 degrees, and then divided by 2 because it is a triangle. So 593.63. And that's going to be square feet. So that's our first piece, but we need to find this second piece over here. Well, to find that second piece, we need to know one of two pieces of information. If we knew this angle, we could find its area by doing exactly what we just did right here. But we don't know that angle, and I don't see a way to find it right now. But there's another way to find its area. If I knew the length of this side here, I would have all three sides, and if we have all three sides of a triangle, we can find the area using Hero's formula. Well, to find this side, I have this information over here, and I can use law of cosines. Remember, law of cosines, if I call this side A and B, this will be side C, and this angle C, side little c squared is side A squared plus B squared minus 2AB times the cosine of angle C. So I can just fill in that information. A is 35, so it's 35 squared, plus B is 40, so that'll be 40 squared, minus 2 times A is 35, times B is 40, and times the cosine of 58 degrees. Of course, this is going to equal C squared. I'm going to enter this all in my calculator all at once, but I'm going to do this as well. I'm going to square root the C squared, so I end up with just C there. So that I get that C equals square root of 35 squared plus 40 squared. Oops, that's not correct. Let me try that again. The square root of 35 squared plus 40 squared minus 2 times 35 times 40 times the cosine of 58 degrees. So I got to close the cosine and close the square root at 36.62. This is 36.62 feet. Now at this point, I could use law of cosines again to find this angle if I wanted to. But I don't need to. I can use Hero's formula for piece 2. So for piece 2, my perimeter is 32 plus 31 plus 36.62, otherwise known as 99.62 feet. Then I have a semi-perimeter, which is half of that. 99.62 feet divided by 2, 49.81 feet. So then the area is that semi-perimeter, 49.81, times the semi-perimeter minus the longest side, 36.62, times that semi-perimeter, 49.81, minus the next longest side, which is 32, times that semi-perimeter of 49.81 minus the shortest side of 31. So second square root 49.81 times 49.81 minus 36.62, close the parentheses, times, open parentheses, 49.81 minus 32, close parentheses, times, open parentheses, 49.81 minus 31. We close the parentheses there, and then we close the square root. 469.14 feet. So our total area is just going to be adding those two together. Which is going to give us 1,062.77 square feet. Now, there's a very good reason why I did this problem. I realized I had not done an example similar to it yet, and this is very similar to question number 3 on the quiz that was assigned yesterday. Next thing I want to review is finding the area of a regular polygon. Remember, a regular polygon is a polygon where all the sides are the same length, all of the internal angles are the same size. So we're going to do, we'll keep it simple and we'll go with a hexagon. So pretend that's regular. Pretend all those sides are the same size. And all those angles are the same length. And let's say that this side, each side of this is 12 feet long. So for this, S equals 12 feet. That's the length of the side. N equals 6. That is the number of sides we have. If you recall, our formula for the area of a regular polygon was the area equals N times S squared over 4 times the tangent, 180 over N. So to find this, for this figure, we fill in the information. N is 6, S is 12, so it'll be 12 squared over 4 times the tangent of 180 over 6. Typically, to do this in the calculator, what we will do is we'll do this much of it first. So I'm going to put in 6 times 12 squared, then divided by 4. Now I can hit enter here and it won't screw anything up. So that's 216. Well, that still has to be divided by that tangent of 180 over 6. We're going to divide by tangent 180 divided by 6. I got to close that parentheses. Gives me 374.12. And that is square feet. So again, the things that can change here is S and N can change depending on how many sides we have and what the length of those sides are. The rest of the formula will stay the same. Of course, this N changes with the other N as well. Finally, let's take our formula that we have for finding the area of a triangle Remember this one here, let's say if this is 48 degrees, and this here is 21 feet, and this down here might be 29 feet. Remember, we found that area was AB times the sine of angle C over 2. So if I label this side A, side B, and angle C, so this would be angle A, angle B, and side C. Whenever we had those two sides in the included angle, in other words, the angle in between them, this formula applied to find the area. So it'd be 21 times 29 times the sine of 48 degrees over 2. Here is 226.29. And those are in feet, so this will be square feet. So the reason I'm going over these things again here at this point is because these formulas are not in the textbook. You could find all of these areas without these formulas. It would just be a lot more difficult. So I want to stop here, pause, and make sure you have these formulas in your notes somewhere. So this here formula is for a triangle where you've got side little a, little b, and angle C. For finding the area of that triangle. So I'll give you a second here to make sure that is in your notes somewhere where you can get to it rather easily. Just like our trig functions where I asked that maybe you find a page at the back of your notebook or even the back cover of your book. Write that down so you have it. Next is this formula here. Let me just do this. It's this formula where n is the number of sides and s is the length of the side. And of course, this is for a regular polygon. So that formula as well should be in that list of formulas that you have that you can reference rather quickly for finding the area, in this case, of a regular polygon. And then an oldie but a goodie that you should have from last semester is good old Hero's formula up here. So make a note that that is one. It still comes into play. It's still going to get used. There's many cases where it has its advantages to be able to use that. A good thing to have in your arsenal. We could use our reverse law cosines to find the missing angle if we want to and go from there. But in many cases, just doing Hero's formula is less work for us. So just wanted to make sure you had those items down in your notes before we moved on. So yesterday we did an example of finding the area of a floor for a house that had an attached garage where the attached garage was at an angle. What we're going to work on today is we're going to work on a similar problem. Where this angle here is going to be 110 degrees. I'm going to give you that this length here is 48 feet. This length here is going to be 24 feet. This span over here will be 28, and this over here, well, let's make it 44. You want to find the area. of the floor. Now, on one of your worksheets from yesterday, there's one where I asked you to find the area of the roof. If we get time, we will go through that example, but it's one that I've backed off in the last couple of years because a roof like that, well, you'd just build it and you'd measure it up if you had to find the area. But for the floor, it is a little bit more practical to be able to calculate that floor area from a blueprint, because in some municipalities, building permits and stuff like that are based off of square footage. So you have to have those estimates before you start building for floor area. So looking at this one here, again, the thing we need to do first is to cut this to pieces. And the logical thing is to cut off these rectangles on either side and leave us with this odd shape here in the middle. Well, what are we going to do with that odd shape? Well, let's look at it. I'm going to draw it out over here. And we're going to look at what we know about it. We know a couple of things. We know angles here. We know these two angles, drawn this well, are right angles. Because, when we cut off those rectangles, those would make right angles. So we know that much. We know this angle here is 110 degrees. Well, then because of that, we know this angle down here has to be 70. Well, how do I know that's 70? Well, that is a four-sided figure. A four-sided figure has an angle sum of 360 degrees. So you can subtract your 90, your 110, and your 90 would leave you with 70 degrees. Alternatively, you know that a full circle here is 360 degrees. Got 90 here, 90 here, and 110 there. This one would have to be 70 degrees to add up to the full 360 turn. So we find it a couple of different ways there. From this shape, at this point, we have the area of these two pieces. Because this time I gave you the front distances rather than the back distances. So we could find those areas, and we will in a little bit. But it's this piece over here that we need to find the area of. And in order to find its area, we need some dimensions. First, we know that this is 44 feet, because that is same as whatever is over there, because it was cut off from that. And this one over here is 28 feet, because of the way it was cut from this garage. At this point, that's all we know. But if you look at this shape is very, very similar to the one that we solved, that problem 3 for the quiz that we started yesterday. So I'm going to cut it up exactly the same way. I'm going to cut it from here to here. Once I've cut it that way, and I already know how to find the area of this piece here. I'll call that piece 3. It's just A times B times the sine of C and then divided by 2. I can find that area, but there's other things I need to find from it yet. So let's find this over here, which I'm going to call little c. So this will be little a, little b, angle c. That'll be little c there. This angle in here will be angle A, this will be angle B. Notice I put them inside because it's just this part of the angle, not the full angle. We know the full angle is 90 degrees. So I can find side C there because I have two sides and the angle in between them. In other words, two sides in the included angle. I can use law of cosines. C squared is equal to A squared, which is 44 squared, plus B squared, so it'll be 28 squared, minus 2 times 44 times 28 times the cosine of my angle, which is 70 degrees. Again, I'm going to do the square root here to get C, to cancel out that C squared. So I'm going to get that C equals square root of 44 squared plus 28 squared minus 2 times 44 times 28 times the cosine of 70 degrees. Close my cosine, close my square root, and I get 43.33 feet for that length of C. Now that I know that C is 43.33 feet, I can find angles A and B. Now I'm going to find B. At this point, I know that they are smaller than a right angle. Both of them are acute, so I really don't have to worry about it. But just because it's good form, I'm going to find angle B first because it is opposite the shortest side. So I have my 43.33. It is across from 70, so that's over sine of 70. This is my law of sines. Equals 28 over the sine of angle B. So I'll cross multiply and divide to get the sine of angle B. Sine of 70, close, times 28 divided by 43.33. Gives you B is 0.6072. Doing an inverse sine of that, second sine of that answer, gives me 37.39 degrees. So B up here, 37.39 degrees. Which makes this angle over here, by the way, 90 minus that, 2.61 degrees. Next, angle A. Well, I'm going to save myself a ton of work. I'm just going to take 180 and subtract these two, which is going to give me 72.61 degrees for angle A. Which makes this angle over here 17.39 degrees. So now that we have that, I can find the missing sides of this other portion of the triangle. If I call this A and B here, I can find those sides. Actually, let me call them something different. I've already got A and B over on the other side. I'll call this D and F so that they're different names. So I have C, the 43.33 over the sine of 110. Is going to equal D over the sine 17.39 degrees. By the way, if you want to double check these angles, you can always add those up, make sure those add to 180 degrees, which they should. So anyway, we'll cross multiply and divide here. Find D. 43.33 times the sine of 17.39. Close that parentheses, divide by the sine of 110. Gives us 13.78 for D. It's 13.78 feet. Which means over here, this dimension is 61.78 feet. I took my 48 and I added the 13.78 to it. And do the same type of calculation for F. 43.33 over the sine of 110 equals F over the sine of, what was that, 52.61. I will cross multiply and divide there to get F. 43.33 times sine of 52.61. Make sure we close that sign. Divided by the sine of 110 gives us 36.64. This is 36.64 feet, which makes this here 60.64 feet. That is just the 24 from down here plus 36.64. You see here is that these can get, this length can get large in a hurry. The mistake I've seen a lot of people make on these is they specify this back wall when they're drawing blueprints. And they might say, well, 60 feet's way too long. I don't need that. I only need, let's go just, 40 feet. That's big enough for a garage. Well, if you only went 40 feet on this dimension here, this dimension up here, right here, would literally only be like 4 feet long. Not what you wanted, right? So it's something, finding these missing dimensions like this is actually a very important task when designing a building like this. So now I need to go back and find areas. So I do have shape 1 here, which was 44 by 48. Which is going to give us 2,112 square feet. And I have shape 2 over here, which is 24 by 28. Giving us 672 square feet. And then I have, from this portion here, I have shape 3 right here, which is 44 times 28 times sine of 70 over 2. Giving us 578.85. And then shape 4. This one up here is shape 4. Probably the easiest way to approach that one, since we had to find all the sides and all the angles anyway, is 13.78 times 36.64. Times the sine of that 110 degrees all over 2. Giving us 237.23 square feet. So we'll add this up to get a total area. $3,600.08 square feet. So kind of a round number for that out of a shape. So hopefully finding the areas of something like that, as long as you see the key, whenever you see something like this, remember we try to cut out rectangles. That's why we chopped off the 2 ends here. And then that odd shape left over, this piece here, you got to be able to cut that up and find the area. And really, there's only 2 ways we could have cut that up. We have the way that we did cut it up, or we could have cut it the other way. Generally, you cut something up, you're cutting it from one vertex to another vertex, or from a vertex to a perpendicular, but there's no right angles in here, so that wouldn't do any good. Not enough right angles, I should say. Some people would be tempted to try to cut this and make rectangles out of this right angle here, or the other way around. Obviously, you're never going to find your missing pieces with that. So it comes down to, again, being able to try different things and divide it up. Knowing how to divide that up really does come from experience and seeing enough of these problems that you know the different strategies. The next example that I want to do today is finding the roof of a house, of an L roof, the area of an L roof house. We've worked on L roofs when we talked about our valley rafters and the difference, the decrease in valley rafters. And we looked at them mostly like this. Or we had them set up like that, and you had to find the decrease in the rafters to go up through there and to go up through here. Find the difference in length, the decrease in length. Well, what we're going to look at today is finding the area of a roof like that. Let's say this is 32 feet here. Let's call this over here 20 feet. Let's make this 56 feet. This piece over here will make 8 feet and 10 feet here. But that means, even though it's not labeled, I'll find them. This, of course, is still 10 feet, the same as this one. This length over here is 28 feet. Because we've got 20 and 8, and that those three dimensions here, these three, have to add up to the whole 56. Now let's sketch this out a little bit differently. Don't really need to see the back side of it. So we can find the area of this roof. Like that is what we're looking at. So we have that this ridge up here is 56 feet. That's from this here. We know that the span across here is 32 feet. We know that this sticks out 10 feet, and the width across here was 20 feet. Didn't draw that scale real well. And really, these two dimensions, this 28 foot and this 8 feet over here, really don't affect our area at all. Now, the one thing we don't have in this drawing over here that I still need is I need some roof slopes. I'm going to say that the slope on the main roof here is 10-12, and the slope on the L roof over here is going to be a 6-12 slope. Well, let's start off with the main roof and the main truss. I'm going to look at this right here. I need to find its height. Find its height? Well, I need its run. This run is going to be 16 feet. So that height is going to come off of my slope of 10-12 equals h over 16. We'll cross multiply and divide to find h. N times 16 divided by 12 gives us h is 13.33. Now, I'm not going to convert that into feet and inches. We know that 0.33 was really 4 inches. It's 13 foot 4 inches. But we're going to be using it to calculate other lengths, so we're going to leave it as 13.33. We want to find this length of this slope. In trusses, it would be a top chord length that we'd be looking for, or length of the common rafter. Here it is still the length of the common rafter, but it's our slope length for our roof area. So that length is going to be the square root of 16 squared plus that 13.33 squared. So on the calculator, I do the square root. I'm going to do the previous answer squared plus the 16 squared, and then I'll close up my root. I get 20.83 feet. So now at this point, I can find the one biggest plane. These surfaces on a roof are called the roof planes. So I'm going to find the area of this backside roof plane here that's this one here on this overhead drawing, which is just a straight rectangle. That area is that 20.83 feet times the 56 feet of length. Giving us 1166.48 square feet of area for that section. Now, The other side over here, this roof plane, is really close to that. It's 1166.48 minus whatever is covered up by this, the L port, the roof from the L coming tied into that. How do we find that area? So what I'm asking here is when we're looking at this roof section, you have this piece here, this piece that's covered up by the L roof. How do we find the area of that piece? Well, we know that the width across here is 20 feet, just the span of that L roof right here. We need to know the height of this. The slant is called the slant height. It's how far it goes up the slope of that other roof. So if I draw my main roof in like this, that L is coming off there. What I need to know is this length here. I didn't draw that very well. Let me try that again. From here to here, that slope. To do that, I'm going to actually come out here on this 20-foot piece. I'm going to look at that. It's a 20-foot span, 612 slope. I'm going to find that height using this 10-foot of run. Well, 6 over 12 equals that height over 10 gives me that height is 5 feet. Well, that height there is 5 feet, tells me that the height here is also 5 feet from the top. So that means right here, this is also 5 feet. I can use that then to find this distance using the fact that this is a 10, 12 slope here. So I've got 10 over 12 equals 5 is now the rise, and I'll call this here y for that run. I cross multiply and divide. 12 times 5 divided by 10 gives me 6 feet here. This is 6 feet. Well, that 6 feet there tells me two things. The first thing it tells me is actually rather important later on. We know that this L sticks out 10 feet. Sticks out 10 feet here, labeled there as well. So 10 plus 6 means that this ridge length is 16 feet. So I'm going to come up here and label that. From here to here is 16 feet, that ridge length. That's going to be important for finding the area of that trapezoid, of that L roof. But the other thing it allows me to do is to find this distance here that I was looking for, that slope. That is going to be the square root of 5 squared plus 6 squared. Giving me 7.81. 7.81 feet. So this is 7.81 feet. So the area that's missing, that's been covered up by that L coming in, is 7.81 feet times the 20-foot base divided by 2, which is 78.1 square feet of area. So that means I have to subtract 78.1 square feet here to get that area of that piece is 1166.48 minus 78.1, giving us 1088.38. For that piece of the area. Well, all that's left here is to find the area of the planes of this L roof. Each of these planes is a trapezoid. Right now, I know the trapezoid has a base of 10 down here, that's just the bottom, and 16 on top, that's our ridge length. We need to know this dimension. Well, that dimension is actually this slope on that 20-foot span over there on the L. So we can find that. It is simply the square root of 10 squared plus 5 squared. And it's 11.18 feet. So that area, 16 plus 10 over 2, the average of the bases, times that height of 11.18 feet. When you add the 16 plus 10, make sure you hit equals before you divide by 2. Otherwise, it'll just divide the 10 and it'll add it to the 16. You'd get something like 21. That's not right for averaging those. The average of 16 and 10 is 13. You take 13 times the 11.18. Because that area is 145.34. So this right here is 145.34 square feet. Now there's two of them. This one over here is also 145.34 square feet. That's all of our areas. So I'm going to take that times 2. I'm going to add the 1088.38. And I'm going to add the 1166.48, giving me a total area of 2545.54. That is my roof area. Another example of this before we're done this semester. Something like this will appear on a quiz at some point too. But for now, let's move on then to the next piece of the puzzle. Look at a roof area. We got a chimney coming out of it. I want that drawn. So let's give us we go a 32-foot span, 40-foot ridge length here, or run. We're going to call this a 1612 slope. And our chimney here is going to be 2 feet by 4 feet. So it is large enough to be a significant chimney. So I want to know, how do we correct or subtract the area of that chimney if we want to do so? Let's find our roof area before the chimney is subtracted. To do that, again, we need to know the length of this slope. And to do that, we look at the common truss. So I'm just going to run my span across there. I need to find this height. I have that run of 16 feet. So I can find my height using my slope. 16 over 12 equals h over 16. And I'll cross, multiply, and divide. 16 times 16 divided by 12 gives me 21.33 feet for h. And we're going to leave that as decimal feet because we're not looking for the actual measurement of the height. We're using the height to find something else. In this case, that slope. That slope, that'll be the square root of the 21.33 squared plus the run of 16 squared. So second square root of that previous answer squared plus 16 squared, and close up my square root. Giving me 26.667. Feet is that slant. Also, our roof area is going to be that 26.667 feet times the 40-foot length times 2, because there's one on the back side and one on the front side. So I'm just going to take that times 40 and then times 2 to get 2133.33. 2,133.33 square feet. That would be the area of this roof if the chimney was not taken out of it. How do we find the area of the chimney, taken out by the chimney? Well, we know the top of the chimney is 4 feet by 2 feet. That area is 8 square feet. But that area is not flat, it's cut out of a sloped surface here. So we need to figure out what area is taken out of that sloped surface. Well, in the truss industry and roofing, there's something called a slope correction factor. What a slope correction factor does is it takes into account something that would be on a flat surface, this certain amount of area, and the fact that when you project it onto that sloped roof, it gets elongated up that slope, so therefore the area on the sloped roof is larger than the area would be on a flat surface. And the way you find the slope correction factor is you actually use the slope itself. This is a 1612 slope right there. So I construct a triangle with a rise of 16 and a run of 12. And I find the length of this hypotenuse, which is just going to be the square root of 16 squared plus 12 squared. Now this one works out pretty neatly. It doesn't always work out so beautifully as that, as to come out to be exactly 20 for that hypotenuse. Once you've done that, the slope correction factor is the hypotenuse divided by the run, the 12. 20 over 12 gives us 1.6667. That is my slope correction factor here. That is saying that if I put something on this sloped surface, on this roof, if it would normally be 1 foot long this way, when I project it down onto the roof, the length that it covers is 1.6667 feet. Well, what makes that slope correction factor so useful is I can now take this 8 square feet from my chimney and multiply by 1.6667, and it'll give me the area that chimney cuts out of the roof. I take my factor times the 8 square feet, I get 13.33 square feet. That's what it actually cuts out of the roof. So I'm just going to subtract this whole area minus the area cut out by the chimney. This is 2,120 square feet is my remaining roof area. So that slope correction factor is a huge deal when it comes into building roofs. So I'm going to talk about it a little bit more. To talk about the importance of a slope correction factor, we need to talk about basically how a little bit of roof engineering, how it's done. Let's just take a basic truss here. And we know that it's made up of certain materials, whatever. And probably some extra webs to make it stronger. Something like that. The loading of a truss. Most trusses are either a 47-10 or 40-10 loading. what this is. The 40 is top chord live load. Live, the term live means a load that is not always there. So that means it could be snow, rain, wind. Wind can push down on a roof. Construction load. While you're building these houses, or when you have to repair or redo the roof, you're going to be on that roof. You're going to have equipment up there, materials. That's construction load. You don't want more than 40 pounds per square foot on that roof for that construction load, or it's over its design limits. I know a lot of people that have their shingles delivered, and they stack them all along the peak of the roof. That's not good. I have seen, it's rare, but I have seen what they call partition separation, where the truss plates start to pull out at the peak because of that extra load. It's too heavy at the peak of the roof. Putting those extra shingles at the peak of the roof is actually the worst place you can put them, because that is the point. A load at the peak of the roof is what causes the most stresses in the webs and everything else of the truss of a load anywhere on that roof. Technically, if you look at specifications, they tell you should stack your extra shingles right down on the gable. And the main reason for that is because it's just right above your support wall, so the truss isn't really holding it. It's the support wall underneath it that's holding it up. But anyway, the 10 here is called a top chord dead load. Dead means it's always there. So this is the wood for the trusses, the wood for the top chord, the wood for the roof sheeting, and your roofing. I'm just going to put shingles here. You're doing a roof, your felt, you got 35-pound felt. That's 35 pounds per square, 0.35 pounds per square foot. Shingles are figured out to be, 250 pounds per square, I believe. So about 0.25 pounds per square foot. The sheeting itself has a weight. I believe the average 4x8 sheet, I believe it comes out to, they figured it 1.75 to 2 pounds per square foot. A half-inch sheeting is 2 pounds per square foot. So if I remember right, it's half a pound per eighth of an inch of thickness is what they figure for sheeting. And of course, nails and stuff like that are part of that 10-pound dead load. The last one, it doesn't really affect us here. This is the bottom chord dead load. Dead again means it's always there. So that's going to be the wood for your bottom chord. It's going to be your ceiling. So your sheetrock or whatever you use for your ceiling, and all your mechanicals. Any vents or wiring or anything like that, it gets strung through the ceiling. I was included in that 10 pounds per square foot. So a lot of times they'll put like an air conditioning unit or air exchanger up in the trusses in the attic of a house. When they do that, it has to be planned to either have a wall supporting it underneath, or they have to specially design the trusses in that portion of the house to handle that extra load. See, a lot of people retrofit a house with an air exchanger in the attic. They don't figure that in, and it causes problems. These plates here that hold these webs on will start to separate because the extra load pushing down here will pull those plates out. Also, the fact those things vibrate quite a bit when they're running, it loosens up those plates. So you really want to do it in a section where there's some sort of a support wall or a closet or something underneath here that's going to help support some of that weight. Okay, so anyway, what was the point of going through all this loading of a truss? Well, it comes down to these two numbers here, the top chord, live load and dead load. When they do the top chord, when they do this loading, they do not account for the slope of the roof. So that square foot is 1 foot in and out, 1 foot wide, but it's also 1 foot flat. So if this is a 32-foot span across here, there are 32 1-foot pieces across here, and they get projected up onto the roof. So when we're doing the loading of the roof, this is 1 foot, not going up the slope here. Well, if we have a 412, 512, 612 slope, it's not a significant difference. But you start getting into higher slope roofs, it is. Let's say we have, let's just look at the weight on a roof. Per square foot of roofing material. As we said, your underlayment is 0.35 pounds per square foot. Shingles are typically rated at 2.5 to 3.5 pounds per square foot. Your sheeting itself is 2.0 pounds per square foot. And nails are kind of negligible. We're going to put them as 1.5 pounds just to round off some of our numbers here. So this ends up being 5 pounds per square foot. The reason there's a 10-pound dead load, there's two reasons. One is some people do mechanicals where they will hang, we haven't accounted for, by the way, the weight of the top part of the truss. That's in that 10 pounds. Usually not that, 2 feet apart and 1 foot of 2x4 is only a couple pounds. So that might, or not even a couple pounds, that might add a pound to that 5 pounds that we have down below. But you also have like strong backs and bracing and stuff like that can be put in there. And you might actually hang some wiring up above to get it up out of the insulation. So there might be some mechanicals that are mounted off of there. The other reason we have such a bit wide thing is the second layer of shingles. You would have, that 0.35 pounds of felt, 2.5 pounds of shingles, and then some more nails. You'd have about 3 pounds for a second layer. When they engineer a truss, they are engineered for 2 layers of roofing. So that's what that weight is for. So anyway, let's just say they're engineered at that 10-pound dead load, and we're going to roof it. There's going to be 5 pounds of roofing on there. But let's say that we have that 1612 slope. Well, we found, actually, let's do a different slope so we can find a new correction factor. Let's say it's a 1212 slope. So let's find this new correction factor. We found the correction factor for the 1612 slope up here. That was the 1.6667. Let's find it for the 1212 slope. So for our 1212 slope, units of rise for 12 units of run. So this here is going to be the square root of 12 squared plus 12 squared. You're at 16.97. So the correction factor is going to be the 16.97 divided by 12. Give us 1.414. That is my correction factor. So the amount of shingles, we would figure this as being 1 square foot. 1 foot in this direction, then of course 1 foot along towards the direction of the ridge. But it's really 1 foot wide by 1.414 feet up the slope, which means the actual amount of roofing material on that is not 5 pounds for the sheeting, the shingles, and everything else. It is actually 5 times that slope correction factor of 1.414, which ends up being 7.07 pounds. Now you can see there, that being 7.07 pounds, if you were to come and put a second layer of shingles on that roof, well, a layer of shingles and felt and nails is about 3 pounds. But again, that's going to have to use that slope correction factor, 1.414, which ends up being 4.24 pounds. Well, that puts us over that 10 pounds per square foot of engineered dead load for roofing and other materials. So on a roof, there comes a point at 12-12 slope, it's not recommended that you roof over the top of an existing roof anymore because your dead load allowance is not enough to account for it, unless some designs will bump up that dead load from a 10 to a 12 once you get above a certain slope. Some of them bump it down to 7 and only design for a single layer even on your lower slopes. So that's what that all comes down to. I wanted to show you that slope correction factor since we've had enough trig now to see how to calculate it and what it means. It's a very handy little tool, because without it, you would have to do a lot of work to find the area of that chimney. You'd have to do a lot of work to find this length and then multiply by the 2 feet. The width doesn't change, obviously. It's still 2 feet wide. But that 4 feet is going to become like almost 7 feet. Actually, right around 7 feet down that slope, like 6.667. So that slope correction factor helps work with that very easily. Where it's even more handy, I shouldn't say more handy, but say that it's not a rectangular chimney. What if we have a round chimney coming out of there? And that round chimney, we draw a little more accurately. Is actually going to cut an oval hole through the roof because of the slope. So let's say that our round chimney is 16-inch diameter. And let's say that this is a 10-12 sloped roof. I want to find the area. And actually, I need to know what size to cut the hole. When I'm cutting the hole, I know that this is going to be 16 inches wide, but I need to know how long to elongate it like this to cut that hole in the roof to run that 16-inch round chimney out through. I'm going to find my slope correction factor here. This is 10-12 slope. So I do 10 over 12. And I'll find this length here, which is the square root of 12 squared plus 10 squared. Gives 15.62. So then we do that 15.62 divided by the 12. You get 1.302. Of course, it's not units on that. That's just the correction factor. So what that means is X here is actually going to be 16 inches times that slope correction factor of 1.302. This is going to make it 20.832 inches. So that's 20 inches. Backed off the 20. Take my 0.832 times 16. That's 13, but now we want the chimney to fit through, so we're always going to round this up. So even though it's 13.3, we're going to round that up to 14, so it's 7/8. 14 16ths is 7/8. So we're going to cut that at 20 and 7/8 inches there. We're looking at calculating roof area, and we want to subtract out the size of that chimney. Well, the area of a circle with a 16-inch diameter is pi times 8 squared. Remember, 8 is just our radius. If it's a diameter of 16, it's a radius of 8. 3.14 times 8 squared gives us 200.96. That's square inches. multiplied by our slope correction factor of 1.302. So times 1.302 makes that 261.65 square inches. And of course, generally we want it converted into square feet. So to get it to square feet, we divide by 144. So it's going to take out 1.82 square feet of roof area. For less than a 2 square foot change in roof area, I'd probably I wouldn't consider that into my roofing materials because I'm going to have to make round cuts anyway. That's part of my waste at that point. Okay, well, I feel like I've been talking steady, and I have for about an hour and 10 minutes here. So it's time to give you guys a little work time. We have skipped our break, so we really only have about 30 minutes of class left. So what I want you to work on is to make sure you finish that quiz from yesterday. Remember, at the beginning of this, the beginning of the day, there were some hints, and actually, number 3 on the quiz was a big one that I started off with. So I will make sure I get this video posted very quickly here after we're done with class. And then also, I want you to finish those 2 worksheets from yesterday. That's all posted in Blackboard under April 12th. Now we are hitting crunch time here. We have just over 4 weeks left. So make sure you are going in Blackboard and checking the grade book. There are 3 or 4 of you right now that are missing a considerable number of quizzes and the last test yet from April 1st. We need to get those wrapped up here and get caught up so that we can finish up the semester comfortably and not have to scramble to pass the class. So with that, I'm going to give you guys, we have about 30 minutes left here. I'll give you that time to get started on those, to work on that quiz or that worksheet. I'll be on the network here to answer any questions for a while if you need anything.